Okay, let's go ahead and get started. Today we're talking about material that'll be relevant for homework 6, which I'll be passing out on Friday. A couple of announcements that I put on the class webpage. We are not having TA office hours this week because the TAs are doing meetings to discuss the midterm. And I sent out something to the announce list yesterday. You should have gotten an email, but if not, you can link it. There's a link here that if you're potentially interested in working for us as a TA in the fall, read this information. We do hire directly out of 143, so that's the only prerequisite for the job. And we hire a lot in the fall, so it's kind of the best time to apply. So if you're interested, check that out. There's a form you have to fill out by Friday at 2. So there's not a lot of time to fill that out. So if you're interested, check it out. Our question of the day had to do with different kinds of loops. For loop 1 out, for each loop is a close second and a few rebels who like the iterator and the while loop. Okay, so let me switch to the overhead camera. We'll come back to the computer later, but let's do the overhead camera for now. Let me try to make sure that I'm looking at the same thing that you're looking at. Okay, looks like we match. So today what I'm going to be talking about is a technique known as backtracking, sometimes called recursive backtracking. This is something that not every university includes in their second computer science class, but it's something that I've always enjoyed having in the class. I introduced this at Stanford 35 years ago, I think, when I redesigned the intro courses there, and they still do a backtracking assignment today, so do we. It opens up some interesting problems. It's a nice application of recursion, so that's kind of why we like to do that. The various problems that we're talking about, you would have seen some in section yesterday. We're going to talk about another one today. We'll be talking about more, another one tomorrow in section, and more on Friday. These problems that we're looking at are things that involve trying to find solutions to something. There's a lot of possibilities to consider, and you need to figure out the ones that actually are correct answers to some puzzle. And humans are really good at solving puzzles. We don't quite know what it is we're doing to solve it. So backtracking is a way of trying to solve a puzzle using an algorithmic approach. And backtracking is a very specific approach. I'm going to tell you on Friday exactly how I want you to apply it in the homework. So in some sense, this could be the easiest homework of the quarter because there's no creativity required. I'm basically asking you to implement a particular backtracking approach. There's kind of no ambiguity about how to approach that. But this is something that's not easy for people. This turns out to be one of the hardest programming assignments for people, and that's because, basically you're learning backtracking. So we don't kid ourselves, you shouldn't kid yourself, that this is going to be a challenging homework assignment. Well, let me give an example first that doesn't involve recursion, and then I'm going to kind of bring it back to that. In section yesterday, we were looking at problems that I would characterize as involving I can spell correctly, exhaustive search, kind of searching and trying all of the different possibilities. Most of the problems that we looked at yesterday in section were like that. Well, let's look at a problem that's like this. What if you wanted to have all 3-digit numbers that included, that were composed of the digits 1 or 2 or 3? So, it could have one of each of the digits like 231, or it could have more than one of them, like 222 would be an answer as well. So 3-digit numbers whose digits are either 1 or 2 or 3. What are all of the possibilities? I could ask you guys to write them all down. You'd be pretty good at coming up with the answers. I think you'd even be pretty good at coming up with a sequential way of doing it. So normally when I have an audience, I ask people, how could we write this code without using recursion, just using things that we've seen before? And people generally think about, well, maybe one of the ways of thinking of it is that the smallest number would be 111. So I kind of want to generate 111, and then 112, and then 113, and then I kind of run out of digits for that third digit. So now maybe I increase the second digit, 121, 122, 123. And if you think it through a little more, people usually are able to come up with the idea that we could write some for loops that would do this. So I could have a for loop, for example, that works with a variable d1 for digit 1, that we start at 1, and we say d1 less than or equal to 3, d1 plus plus. So we'll have kind of a for loop that's going to get us all of the different possibilities for digit 1. And inside of that, there could be a for loop that had all the possibilities for a digit 2 less than or equal to 3, digit 2 plus plus. And then inside of that, there could be another for loop that gets us all of the possible third digits. Say a digit 3, d3, d3 less than or equal to 3, d3 plus plus. And then inside of here, the idea would be that I will have chosen a D1 and a D2 and a D3. Like initially, this nested loop structure is going to generate 111, which is what we said was the smallest number that's of this form. So maybe we'll just do a println in here. System.out.println. How do I print this? Can I print D1 plus D2 plus D3? I mean, you know that's not right. That gets you the sum of the digits. We got to kind of put them together. This is a place where we can use that trick that Kai Horseman had mentioned, where we do quote, quote, plus, that we can take an empty string and concatenate D1, and then concatenate D2, and then concatenate D3. So we can kind of put the three digits together. We need some closed curly braces for these different for loops. So what is that going to do? It's going to, the first for loop is going to set D1 to 1, this is set D2 to 1, and then D3 will go 1, 2, 3. We'll get 1, 1, 1, 1, 1, 2, 1, 1, 3. That's what we get with that inner for loop executing 3 times. And then we have kind of run out of that inner for loop, so we come back around to the middle for loop. This is where we would kind of change our second digit. We'd increment it to be a 2. So now we're going to look at things that begin with 1, 2 as that middle digit. So we would have 1, 2, 1, 1, 2, 2, 1, 2, 3, because we execute this inner for loop, for its 3 different possibilities. And then we would come back here, and we would have things that begin with 1, 3, etc. So 1, 3, 1, 1, 3, 2, 1, 3, 3. So I think you can see this is going to kind of do what we want it to do, to generate the various different possibilities. I want to talk about this, several things related to this. One of them is that I wanted to mention the idea that we often think about what you might call a search space, that we're thinking of some set of possibilities that exist. Like, for example, here, I might say that my search space is the space of all 3-digit numbers. There's lots of 3-digit numbers, some of which satisfy my constraint that they're composed of just the digits 1 and 2 and 3. But the general search space might be bigger than that. So, we have kind of the idea of lots of possibilities, and we're looking for what we would consider a solution. There's some criteria that say that this is a legal solution that we're looking for. In our case here, things composed of the 1s and the 2s and the 3s. And often what we do when we're thinking about this, and this is kind of what we do with the exhaustive search, but it's going to carry into backtracking, is that we think of this as a series of decisions. And we put together what I would call a decision tree. So what is it that I'm doing here? I'm kind of imagining that D1 is making a choice for digit 1, D2 is making a choice for digit 2, and D3 is making a choice for digit 3. I'm going to once again anthropomorphize these different, what are going to become recursive calls. Here, just in this case, the individual for loops. If I had an audience in front of me, I might point at people in the front row and say, I want you to be D1 and you to be D2 and you to be D3. Maybe I'll just kind of put some little stick figures here. Suppose this is going to be our D1 person, and this is going to be our D2 person, and this is going to be our D3 person. So I kind of have three people together solve this problem. And one of the ways you can think of it, let me get just a little bit more, being able to see what's going on here, is that you can imagine that I say to this D1 person, I want you to consider all of these different choices. And so this D1 person might say, well, I choose to start with a 1. And then I say to the D2 person, I want you to make all of your different choices, and this person begins with a 2. And then I say to this person right here, I want you to consider all of the possible choices for the third digit. Oop, that's supposed to be a 1. What am I doing? I'm thinking of the variable name and not the values. We begin with 1, 1, 1. That's what all three of them kind of start with. And then that gets us to our first println, right? And then what ends up happening is that this person who's making the choices for the third digit would change this to a 2, and we have 1, 1, 2. They change this to a 3, and we have 1, 1, 3. Then this person is done, so we come back here and we say we want you to move to your next choice. So they'd move to a 2, and then this person starts all over again with 1, 2, 1, and so forth. So you could kind of imagine them holding up cards or something like that to show the choices that they're making. I don't know about you, but when I visualize this, one of the things that I found helpful is I kind of think about mechanical counters. Maybe it's because my brother took apart a lot of stuff when I was a kid, and so I saw all the stuff in his room, things he'd pulled apart, including things that had counters like this. So I kind of imagine that this rightmost digit here, that's like D3, and that this digit here is D2, and this digit here is D1. So the way these counters work is you have these wheels that turn. And so I kind of see this, there's a third wheel here that goes 1, 2, 3, 1, 2, 3, 1, 2, 3. It's kind that's what we would see going on with this person if they were kind of holding up a card that said 1 or 2 or 3, is that they'd be going at a very steady pace, 1, 2, 3, 1, 2, 3, 1, 2, 3. And then the next one over goes more slowly, that it's only when this one has completed its cycle of 3 that we go, so it kind of goes 1, 2, 3, 1, 2, 3, right? I mean, it turns more slowly because it has to wait for this one to finish its cycle. And then this one is going to be the slowest one of all. 1, then we wait a long time for the other 2 to finish. 2, we wait a long time for the other 2 to finish. 3, so it's kind of the slowest one of those. So I don't know if that's a helpful way of thinking of it or not, but I like to visualize kind of the counters, and I think of these as being like those different wheels on the counter, So in terms of a decision tree, we would say initially we hadn't chosen anything, and so then what we do is we choose either a 1 or a 2 or a 3. That's the choice that we make for D1. And then once we've made a choice so that's kind of that first robot making a choice. Suppose it picks a 1. Well, then there's kind of this middle robot that kind of makes choices of a 1 or a 2 or a 3 for digit 2. I'm going to run out of space here. You can see, I should have pushed this over to the right a little bit. But I'll show you. I've got a picture of this that I'm going to show you in a second. And then, so suppose D2 has chosen 1. Then we kind of have, the choices of 1 and 2 and 3 for what are the different possibilities for D3. And so, kind of expressing this in a tree-like form, we want to kind of show when no choices have been made, and then we chose a 1 for digit 1, we chose a 1 for digit 2, we chose a 1 for digit 3, that was the 1, 1, 1 possibility. Now, what ends up happening then, in our code case, we printed out the 1, 1, 1. And then what happened? We came back around our inner for loop. Well, in terms of the way I would describe it with this diagram, is that we've completed this possibility, exploring this possibility, so we come back to where we were before and we say, were there any choices left? There were. So we hadn't explored the possible choice of 2. So that gets us to 1, 1, 2 as another possibility. And then we print that out. And then we come back and we say, are there still choices to be made here? There are. We could have chosen a 3 for the 3rd digit. So we're exploring 1, 1, 3 as a possibility, and we print it out. What happens then is a little more interesting, is that, then I've kind of finished this particular choice here, so I come back to where I last made a choice, and I say, are there any choices left here? And the answer is no. So we back up again to where we last made a choice, and we say, are there any choices to make at this level? The answer is yes. We had chosen 1 as our first digit at this level. Now we choose a 2. And that's like coming back to this middle for loop and incrementing D2 by 1 to kind of consider, another choice there. So that's where this term backtracking comes from, is that we're considering a series of choices that get us to a possible solution that we're exploring. And when we've finished exploring that, we back up, we backtrack to where we last had a choice. And we kind of continue with a brand new choice. So that's the backtracking idea, is we kind of back up to where we were before. Now, obviously, these decision trees can become gigantic. Even in this small case, take a look. I actually made a version of the tree, and you can barely read it. It's so tiny. But this is kind of that complete tree, that has a depth of 3. There's our choice: 1, 1, 1, the triple 1, then 1, 1, 2, 1, 1, 3, and then we back up to here, we choose a 2, and we do 1, 2, 1, 1, 2, 2, 1, 2, 3. We're done with the 1, 2 possibilities. We come back, we're going to do the 1, 3 possibilities, 1, 3, 1, 1, 3, 2, 1, 3, 3. We're done with those, and then we back up to here, and there weren't any choices left to here. So now we finally make it back over to here. It's like that 3rd wheel finally turning. And this one we move to a 2. So now we're going to explore things that begin with a 2, and there's a whole bunch of things to generate that begin with a 2. And then once all those are done, we back up to here and we explore things that begin with a 3. So that's kind of the idea. That's the picture we're drawing with these decision trees. I think it's helpful for you to understand these decision trees. I asked the TAs to spend some time on this in section. And there was a handout. It's linked on the sections page. If you didn't get it already, it's still there. So if you go to the sections page, it has 3 of the problems from section yesterday, and it shows you decision trees for those problems. Now, I mentioned that most of them involve this exhaustive search aspect to it, but some of them involve what we would call a dead end. So that's another important concept to understand with a backtracking type solution. And so kind of the nice one for that is this one that involved starting at 0, 0, starting at the origin, and trying to move within the Cartesian plane. So the idea I had was that there were 3 possible moves you could make. You could either move north, you could move east, or you could move northeast. Moving north increases your y-coordinate by 1 because you go up. Moving east increases your x-coordinate by 1. And northeast is kind of the diagonal move that increases both of them by 1. So the idea was to explore the possible places you could get to, or how to get from the origin, starting at 0, 0, to get to a location like this x location of 1 and a y location of 2. And so, the backtracking approach, it basically ends up making the choice that's like the 1, 1, 1. We choose north, north, north as the first possibility. That gets us to having a y-coordinate of 3. Now, this northeast, northeast thing, x's and y's are always either staying the same or going up. They never go back down again. And that y-coordinate is larger than the y-coordinate we're trying to get to. So we've overshot the y-coordinate. We've gone past where we want to get to, and that's a classic dead end. That's not going to work out. There's no reason to continue exploring from here because we're past where we're trying to get to in the y-coordinate. So that's a dead end. This one turned out to be not a dead end, which was choosing north, and then choosing east. So kind of the middle one of these led to actually a solution. That's why it's in red with a little dash thing here to indicate that it's a solution. This was a dead end as well. Now, so here we're not going to a particular depth. We just kind of explore all of the different possibilities until we either get a solution, which there's several places here where we end up getting a solution, or we reach a dead end. And when we stop when we reach a dead end, because there's no point in exploring beyond. So this is closer to the classic backtracking approach, where we're not going to some specified depth. We're basically just kind of continuing until we either find an answer or we find a dead end, and then we stop. So we have kind of a truncated tree in a lot of ways, because there's a lot of dead ends that we reach along the way. And so we don't want to continue past the dead ends. All right, normally I'd ask for questions, but I don't have the opportunity to do that. So let's move on. There's a problem that I want us to discuss. It's basically a classic puzzle that's often called the 8 queens problem. It involves placing queens on a chessboard so that no 2 queens can threaten each other. This 8 queens problem that we're going to go over is a model for you to understand for your homework assignment. I've often had students come, say, to my office hours, and they are having trouble, and I say, well, okay, let's talk about 8 queens. You know, how does this relate to 8 queens? And they say, well, I never understood the 8 queens. Well, that's not an acceptable answer. You're not allowed to not understand 8 queens. Particularly in Friday's lecture, I'm going to show you a very strong relationship between the 8 queens approach and the problem that you're going to be solving in the homework assignment. So it's really important to understand this. We're going to take a lot of time to explain it to you. I'm going to do things in the lecture today and on Friday. You'll have a section tomorrow where the TAs will be going over another backtracking problem, and they can conceivably answer some questions then too. So we want to solve a more generalized problem where it's kind of n queens. Let me think about the 4 case. So let me kind of draw a chessboard that would be a 4x4 board. And I'm not assuming that you guys necessarily know how chess works, how queens work. So let's talk about it. So let me see. I'm going to call this column 1, 2, 3, and 4, and row 1, 2, 3, and 4. So suppose, for example, that I placed a queen right there in row 1 and column 1. Queens are very flexible pieces on a chessboard. A queen can move anywhere in its row, it can move anywhere in its column, and it can move anywhere in its diagonal. So if there were another queen, say, right here, or another queen right here, then this queen would threaten that queen because it's in its row or column or diagonal. So the idea is to place 4 queens onto this board so that no 2 of the queens threaten each other. So how could we do that? So I've got a queen here. Normally what I do is I ask the class to give me suggestions. Tell me a row number followed by a column number. So like, is there a place we could put a queen in row 2? Well, it can't be there, it can't be there. But I could put a queen here in row 2, column 3. I think that works. Let's see. I think actually that I can put a queen here. It's nicer when I get to ask students this, because that way if it's wrong, I get to blame you guys. And I have a whole classroom full of people who are checking to make sure that this is true. I don't think this queen is threatened by either of these 2. This one is in this diagonal. This one is in this diagonal. So I think that's actually an okay placement for a queen. So where do I place the fourth one? And so I wait and give people a chance to think about it. Well, it turns out that there isn't a good place to place the fourth queen. One of the ideas that's going to be an important idea to understand, and I think it's how you might approach a problem like this if you were working on it yourself. So I put a queen here, right? So you could imagine erasing that queen. That's going to be something that we're going to refer to as unchoosing. That's going to be an important concept in what we're going to be doing, is that sometimes we say, well, that didn't work out, so let's undo that choice. And is there some other possibility? We can try various things, and what we would find is that we need to kind of undo this choice too. And we can try various possibilities here, and we're going to find that this was the mistake in a sense. You know, I screwed you guys over to begin with by putting a queen in the corner. I happen to know that there is no solution to the four queens problem with a queen in the corner. So that original choice has to be undone, and we have to go back to choosing positions that don't involve having a queen in a corner, because that just doesn't work. So again, you know, if we had people here, you guys could give me your choices. There's a symmetry to the board, so you know, placing a queen here isn't going to work out, or this corner, or this corner, or this corner. None of the corners are going to work out. So what if maybe you put a queen, say, here? Then where else could we put a queen? Maybe we could put one over here, and then I think we can place a queen. Let's see, how about here? I think we can place a queen. I don't think that, so this is this diagonal, this diagonal. I think this one is okay. And I think we can place a queen down here, if I'm not mistaken. So again, if I had an audience, you guys would keep me honest. We'll see in a little bit, because we're going to look at a program that actually does this exploring for us. But I think I got that right. I think I've got a solution to the four queens problem there. So that's the kind of thing that we want to think about, is how do we use a backtracking approach to be able to figure out where to place n queens on an n by n board. Well, let's talk about the idea of decisions and backtracking. So in the more general case, what we would have is a great big board. I'm not going to draw a full 8 by 8 board, but maybe I'll put a few columns and a few rows in here. So there's going to be some different columns here, dot, dot, dot. There's going to be some different rows that are here. So I'm not drawing out the complete chessboard here. I'm just kind of showing you a partial board, dot, dot, dot. You know, there's going to be more things in those different directions. So if I was going to think of this in a backtracking way, and I wanted to come up with a decision tree that allowed me to think about kind of a sequence of choices that are being made, I'm always a little surprised. Maybe it's because, you know, I think that when you've done a lot of backtracking problems, it kind of becomes a little obvious to you what the individual choices are. But I'm sometimes surprised that people don't see what the choices are here. Well, I mean, it's not so surprising. You're learning, so it's not surprising that it's not necessarily, you know, kind of clear. But in the way that I was describing it, I place a queen, you know, a first queen. I place a second. I place a third. I place a fourth. Those are my choices. Where to place the first queen? Where to place the second queen? Where to place the third queen? Those are the decisions that I'm making that lead to my kind of tree-like structure. So how many places are there to put a queen on an 8 by 8 board? Well, there's a lot of them. So basically, you know, there's like 64 different spots where I could place a first queen. So I could consider all of that. You know, this would be one way to do the backtracking, is to consider the 64 different possibilities. And so suppose that I think about this particular one. You know, this is a particular square of the board where I've placed a queen. How many choices are there to make for the second queen? Well, there's again still a lot of different choices to be made. there's 63 spots left because this queen is filled, I've put one queen on the board, there's 63 empty spots that are left. Well, this is a gigantic decision tree, and it is true that backtracking is a brute force technique, and we often do tons of searching. I think that one of the things that people find hard about backtracking is that you want to make it more efficient than it is. So it is an inefficient approach. It does check lots of possibilities, and we're generally okay with that. But this one, we can apply a little bit of intelligence to do something better, quite a bit better than doing 64 possibilities times 63 times 62 times 61. We don't have to explore all those possibilities because a lot are dead ends, but that's still a lot of possibilities to explore. Well, we want to apply a little bit of logic here to do somewhat better than this. And so I usually ask the class, is there something that you know about this solution that would allow you to limit the different choices to consider? And people usually come up with the idea, think about the different columns of this chessboard or the different rows of this chessboard. It's basically an equivalent way of thinking of it. I like columns, so I'm going to think of it the column way, but the row way of thinking of it is perfectly fine. What will be true of column 1 if I have a solution to the 8 queens problem? Well, there's going to be a queen in that column. Well, let me say it the other way. There won't be 2 queens in the column. If there were 2 queens in the column, then they would threaten each other. So there's no more than 1 queen in the column. And if there are n queens with n columns, and I can't have more than 1 queen in a column, then I have exactly 1 queen per column. So any solution to the 8 queens is going to involve a queen in column 1, a queen in column 2, a queen in column 3, etc. Exactly 1 queen per column. So that's the way I want us to solve the problem, is to kind of do it column by column. So in column 1, for example, if I think about this, how many different possibilities are there? Well, it's basically these different rows, that I could put a queen here, for example, or I could put a queen here, here, here. How many different choices are there? There are 8 different rows to consider. That's a lot better than the 64. So there's 8 places, 8 different rows where I might place a queen. Let's think about, here, let's suppose we think this is placing the queen in row 1. Suppose I'd done that. How many places are there to place a queen in the second column? And I often have students who'll give an answer like 6. And I think that what they're thinking about when they say 6 is they say, well, you can't put a queen here because they would threaten each other. You can't put a queen here because they would threaten each other. So there's only 6 possibilities. But I think that it's kind of better to think of it as there are 8 rows. There's always 8 rows. We're always considering 8 possibilities. But some of those possibilities we're going to quickly reject. So we will consider row 1, but we'll find it's a dead end. We'll consider row 2, and we'll find it's a dead end. So we're going to consider them, but we'll quickly reject them. So there's 8 possibilities here, 8 at the next level, 8 at the next level, and so forth. Now, the way that this is going to going to translate into recursive code is that each of these choices, the choice for column 1, the choice for column 2, the choice for column 3, each choice is going to be made by a different recursive invocation. So I'm again anthropomorphizing, thinking of it as robots that have been programmed with an identical bit of code, or people who are involved in this problem. So a first robot is going to consider the 8 different choices you could make for column 1. And then a second robot would consider the 8 choices for column 2. A third robot would consider the 8 choices for column 3, and so forth. So that's the way we're going to approach it. We're going to write code in just a minute. When I was at Stanford, I had a colleague that I co-authored a textbook with, a fellow named Steve Fisher. And he had an interesting observation about these backtracking problems, is that he said that often students get lost in the details of keeping track of the specific backtracking problem. Like in this case, there's the idea of a chessboard. We don't have to have a generalized chessboard, but we need to keep track of a chessboard where we place multiple queens. Where have you placed queens? Does this queen threaten the queens that are already there? And his point was that it's good to have supporting code that takes care of all the low-level details. So I've done that for 8 queens. I'm going to have a board class. And the board class is going to have a constructor that takes a size. And normally I ask the class for suggestions. What would be things I'd want a board object to be able to keep track of for me so that I could be doing things like this, putting a queen in some place in a column, considering other possible placements in other columns. Kind of the most basic thing is that you're going to want to be able to place a queen at a particular row and column and have it remember those placements. But we're also going to want to know, is it safe to place a queen at a particular row and column? Because that's the dead end idea. We want to make sure we don't place a queen in some place that's going to be unsafe. And it may not be obvious, but remember what I was doing back here, that I kind of crossed out the old one, erasing where I had placed a queen before. We're going to want to have a remove command that allows me to remove a queen that I had placed in previously. I included something where the board would remind me what its size is. So, because there's going to be different sizes. There's 8 is standard, but it's the n queens problem. And some way to see where the queens are placed, I decided to just have a simple print command that would print out the positions of the queens at any given point in time. So I have a board class that has these methods. I'm going to show you a little something with it in a second. And this is what we can use then to solve the problem. As we solve this problem, basically, what am I going to have to tell each of the different recursive invocations, each of the robots who's working on this problem? Well, I'm going to have to give them access to the board. They'll need access to that in order to solve the problem. And each different queen is going to be working on a different column. So I'm going to have to tell each queen what column to work with. So I think that's enough that I can switch over to the computer. So let me switch to the laptop and send it to the projector and make sure that we're looking at the same thing. So the board class is something I'm going to put on the calendar for today in case you're interested. And I included in it what's known as Javadoc Comments that allow you to make a nice HTML version here that shows you the place and print and remove, safe and size commands, the constructor that takes a size. This will be linked from the calendar for today too. So I'm giving you an example of a program with Javadoc Comments. Javadoc Comments make these beautiful HTML files, which is nice, but I don't tend to push them a lot because I don't think they're that readable in an editor like JGrasp. But they're obviously very useful. So anyway, you'll have an example of that in the board class. And what we're going to do then for the rest of the lecture today is to finish out this queens program that's trying to solve the queens problem. It calls a method solve that passes in the board, and this is going to be kind of my public method, that starts up my private recursive method. So in order to solve the board, I'm going to need to pass along the board and to tell it what column is the starting column. So this is going to be my recursive method, this explore method, where I give it the board to work with and I tell it what column to start with. So imagine that the way 8 queens is going to be solved is I'm going to say to a first robot, you work on column 1. It's going to ask a second robot to work on column 2. It's going to ask another robot to work on column 3 and so forth. And we want to do this in such a way that we're not exploring dead ends. So this kind of has implications for what we want to have be true of the preconditions and postconditions for this method. So let's think about a kind of a typical case in the middle. So suppose you're going to be the robot that I ask to work on column 5. Suppose we're solving 8 queens, but I ask you to do column 5. Well then, what is it that we want to have be true if I'm going to be asking you to do column 5? Well, I'm going to want to have filled up the prior columns with queens that don't threaten each other. So I'm going to say all columns less than col have a queen so that no 2 queens threaten each other. So if you're going to be working on column 5, I want it to be the case that 4 other robots have placed queens in their columns. So that we've got 4 queens that have been placed, you're working on the 5th, to work on this particular column. And so what are you going to do? Explores all possible placements of queens, starting with column call, and printing all solutions it finds. So that's kind of a description of what it is that we're going to want to do. So think about this, the explore command. So I'm going to say to a robot, you work on column 1, and it's going to kind of call up another robot, you work on column 2. And it's going to call up another robot, you work on column 3. So we're getting to higher and higher column numbers. What would be a nice column to get to? So what would be a nice place to get to where we'd be pretty happy? And what I usually have people say is, well, if you get to the point where column is equal to 8, if you get to the 8th column, that's pretty good. Now, we don't want to use the number 8. We want to use b.size because we're trying to do the general purpose solution, not just 8 queens, but n queens. So if you ever got to something, like in the 8 queens case, if you got to column 8, that would mean that 7 queens have been placed, so that they don't threaten each other. What's even better than getting to column 8, and it's getting to column 9? So kind of getting beyond. So what I'm going to say is if the column number is greater than the board size, if I've gotten to column 9, that means I found a solution. That means that I have placements of queens, that don't threaten each other in all of the columns. So I'd want to do b.print, because this is the kind of the hooray, we found a solution. Let's print it out. So that would be our base case, is that, if we get to the point where we're beyond the size, we want to just print it out. And otherwise, what is it that we want to do? So otherwise, it would be a case like the column 5 case, where I've asked you to think about column 5. So what are you supposed to explore? Well, you're supposed to explore the different rows, row 1, row 2, row 3, row 4. How do you do a bunch of different rows, like that? Well, a for loop is good for that. On the exam, I told you that for the recursion problem, you couldn't use any loops. But that's not true of homework. I mean, if there's a place where a for loop is helpful, go ahead and use a for loop. So I can say for int row starting at 1, row less than or equal to the board size, row plus plus, I want you to kind of consider the next possibility. So that's like my decision tree having all those, those 8 different, branches that come from it. So, and how do you explore a possibility? Well, in general, normally I ask the audience and I get, good answers from people, but, in general, we're going to want to be thinking about placing a queen. We're going to want to think about placing a queen at that row and column. But remember what I had talked about, that in column 1, I put a queen in the upper left corner. And then when I went to column 2, remember that we said that those first 2 rows we don't want to spend time on because they would threaten the queen we placed in column 1. So those are dead ends that we don't want to explore. So we don't always want to place. We want to make sure that we haven't reached a dead end. So we want to know, is it makes sense to place a queen at that spot? And the way to know that is to call the safe method. Is it safe to place a queen at that row and that column? In which case I'm going to consider that possibility. So you only want to explore the placements where the queen doesn't threaten the ones that are already on the board. So it would be a dead end, if we come across a spot where it's not safe to place a queen. And we don't want to explore those dead ends. We want to just move on to the next possibility, come back around the for loop, and kind of do the next row number. All right, well, what do we do here? We place a queen. So suppose that you are the column 5 robot. So there were 4 robots before you who placed queens in columns 1 through 4. You have placed a queen in column 5 such that it doesn't threaten the other 4. There are now 5 columns in which there are queens placed that don't threaten each other. Now, you might imagine that you now want a for loop for column 6, which is going to require a for loop for column 7, which is going to require a for loop for column 8. for loop for column 8. That's that non-recursive thinking. That's that rabbit hole that you don't want to go down. No, if you've placed a queen in column 5, you've placed a queen in column 5. So now there are 5 columns that have queens placed in them. If only there were a method that could explore what's left, then I could call it. That I could say explore using this board, and now that I've placed a queen in column 5, I want the next recursive invocation to start at a column 1 higher. So I'm going to give it col plus 1. I ask a robot to start in column 6. So the robot doing column 5 finds a legal placement and then fires up the robot that's going to think about column 6. That's kind of what it does. As I've said before, don't say col plus plus. Just think about it. I mean, as you go around this for loop, you don't want to be incrementing col as you go through. Col plus 1. When we do these recursive calls, we tend to use plus 1 to pass on to the next level, a new value. Not, plus plus is going to lead you astray. Don't write code like that. Now, you might think that this is enough, but it's not quite. Because what ends up happening is, so suppose that I place a queen, in a certain row, and I go off and I explore. And now I come back. Well, I'm going to come back around my for loop, and I want to consider the next row down. But I have a queen that I've placed in the current row. So before I go to the next row, I have to erase. I have to undo what I did. So I have to do a remove at that row and call. This is something that the TAs and I will kind of sometimes refer to as the backtracking pattern, which is choose, explore, unchoose. Choose something, explore the other possibilities recursively, and then when you come back, do any cleanup that requires unchoosing. Often there isn't an unchoose. Often there isn't anything that you have to do. But for your homework, there will be an unchoose. For one of the problems on the section tomorrow, there's an unchoose step. So sometimes there is an unchoose that needs to be done. But otherwise, we're basically done. The backtracking code becomes very, very simple. We're checking for dead ends. We are using the backtracking pattern, choose, explore, unchoose. We've identified a base case, where we would know that we had an answer. And so if I run this version and say do 4 queens, it comes up with these 2 solutions right here. I think this, I'm not sure whether that was one of the ones that I had or not. Maybe I didn't have a solution to the 4 queens. Could be. Anyway, you can check it out. I'm going to put another version of this on the calendar for today. That an interesting thing about this is that it's a variation where I use a different kind of object, a board frame object. You might wonder how I can have board over here and board frame over here. I used inheritance. So I used inheritance to create a variation on it. And in this variation, I do graphics type things. So that basically what it's doing is it's showing you the computation as it's doing the 4 queens. When it asks the safe question, it puts that little question mark. That little undo command is what happens when you do a remove. So it's exploring all of these different possibilities. It's going to run out of possibilities here, and it's going to undo this. That doesn't work. That doesn't work. It's going to undo this, come back and undo this. That's going to lead to a solution eventually. There wasn't one with 1 in the corner. So you are watching backtracking execute as it goes through and explores different possibilities. I think this one's going to work out. And so then it gets to column 5, and it prints it out in a little happy face, that we get in this graphical version of it. So as I said, I'll put this up on the calendar for today so you can kind of watch this backtracking live. You can kind of see it as it's doing different possible choices here. I think of this again as being a little bit like my counters where, or think of this as my D1 loop, my outermost for loop. It's going to take a really long time before this process reaches a point where it comes back here and asks the for loop to come back around and consider row 2. There's tons of possibilities. Look, it's only in row 3 over here. Let me speed this up a little bit so we can watch it go a little faster. In fact, I'll do the maximum speed so that it'll maybe before the thing cuts off, we'll have enough time to see a solution. But it's going to just go through, look for different solutions. When it finds one, it does the smiley faces. Again, I overrode the print command so that it did the smiley thing. You are watching backtracking by running this program and observing. It'll be on the